Let's start working with our producer. So we're going to start filling the blanks here. Creating a brand new shared memory segment. So refer to your documentation, to the reading assignment, etc. What it boils down to is to get a SHM ID, a shared memory ID, from the SHM get system call. So we're going to use SHM get. We specify our key, SHM size. We specify the size that we want, and we specify protection right, access right, okay? And then we test if everything went okay. If SHM ID is less or strict than 0, then we have an issue. P error, unable to create brand new shared memory segment. And of course, we are going to exit the program here, exit failure, and we are done for this first step. Okay, so that is the first step. The second step consists in attaching the shared memory segment to our address space. So pretty much we are going to get out of that what? We are going to get a pointer. So let's go for it. We have already our variable of type pointer. SHM at attach is a system call we want to use, and we are going to use a very basic way to attach a shared memory segment, which is, I don't care exactly where you put it, just return to me the address where I can access it. And we are going to check also that if SHM equal -1, so if the value returned to me seen as a char star, because this is a type of my variable, is -1, then there was a problem. P error, unable to attach shared memory segment. Exit failure as usual, and that's another step handled, and a system call checked for correctness. What else? Well, we are going to get our shared memory segment here. We are going to attach it. And I'm double checking here what I did with this get. Yes, I did what I suspected I did. I specified the access right, but I didn't specify the IPC underscore create option, which means I want to create a brand new shared memory segment. So this is fixed. So I want to create a brand new memory segment with this specific access right. I attach it, and now I'm ready to go and work with it. What does that mean to work with it? Well, I have already here in this loop everything I need except writing the value of I to this shared memory segment. Well, star SHM equal I. What is important to understand here is that once you have a pointer, you can simply dereference this pointer as you would dereference any pointer in this language. So this is how you are going to use actually a shared memory segment, through a pointer and by dereferencing it. So in this case, we do star SHM equal I, we dereference our pointer, we write the value of I. I'm going to change something that I don't like, and I already mentioned. Instead of using here this char for a small int, I'm going to use a full size int, since we allocated anyway here a shared memory segment big enough to hold an integer. So that means that I need to change the type of the pointer SHM. Here star SHM equal I makes suddenly a lot more sense, and here I need to modify this into int star. There we go. So let's save. So that's our producer, and this is pretty much almost everything. I'm scrolling down. We need to detach our shared memory. Well, this is going to be achieved by SHM DT, to which you pass the pointer of the shared memory. Not the key, not the ID, but the pointer. Destroying the shared memory will be a matter of calling SHM control with your SHM ID. IPCRM ID as command, which means destroy. Okay, we can do many more things with SHM, sorry about that, SHM CTL. With SHM CTL, here we use it mainly to destroy our IPC mechanism resource. So in this case, destroy our shared memory. And we are done with all the steps for our producer. Before to go further, let's just compile real quick so that we make sure that syntactically we didn't introduce problem. So this is our producer v1.c. Syntactically it seems to be working. So now let's go back to the consumer and let's do the same type of work. So in the case of the consumer, I'm going to use cut and paste because this is really the same thing. We are going to first, let me grab this here. We're going to first open an already existing shared memory segment. Well, SHM ID is going to be assigned to the value returned by SHM get. And here I don't need to specify IPC_create. I don't need to specify an access right. PError exit. This is a classic error handling. There we go. And that's it. Attaching the shared memory segment is going to be exactly the same thing than for the producer. Okay, down to the check for validity of the attachment operation. So I'm going to have here SHM equal SHM attach. Okay, same option. I'm going to modify like I did for the producer. Sorry, modify the type of the variable SHM, which is a pointer on int, and I'm going to handle the same way here any error that will pop up. And a little bit of indentation here to just make it a little bit more readable. Okay, so I have my attachment step. Now I'm going to read data from the shared memory. Well, how do you read data from the shared memory? The same way that you write. Once you have this SHM pointer, really there's nothing new anymore. What is new to you is how to set up shared memory and how to dispose of it. But once you are using shared memory, it's really just pointer arithmetic. And then we need to detach our shared memory. Let me save. Let's go back to Conqueror and check how we are faring for syntactical level on consumer v1. Let's see. That looks good. So let's compile our two prod v1.c, and I'm going to name this executable prod v1. Then I'm going to compile gcc cons v1.c. Oops. Let's see, and call this executable cons v1. Now I have two executable. I need to run them in parallel in two different windows, right? So I'm going to go into Tool, Open Terminal. Okay, here's the first terminal here. I'm going to open inside this terminal another tab. So I'll have like two windows for me to work with. I will execute in each window one of our program. Let's call this tab producer, and then I'm going to create a new tab which I'm going to call consumer. So it would be difficult to be clearer than that. In the producer tab I'm going to execute prod v1, enter. What key should I use? Well, I'll come back to that in 1 second. In the second I'm going to use cons v1. Alright, so the producer, what key should I use? Let's go easy. 1, 2, 3. Enter. The producer is starting to work. Quick. 1, 2, 3. Same key for the consumer. Alright, let's observe what's going on now. Producer, I wrote 0, 1, 2, 3, 4. So the producer seems to be working. Writes the numbers in order. And every time wait a variable amount of time. What about the consumer? 1, 2, 3. I missed the 4. 5, 6, I missed the 6, 7, 7, I read twice the number 7. Why? Why does inconsistency? Because I read 7, I slept for only 2 seconds. You can bet that after writing 7, see, the producer was waiting for a little bit more than that. So that means that I read again, I was ready to consume a new value when the producer didn't finish producing one. And I missed some value because, of course, if the producer produces too fast, well, it produces 8, I read it, then it produces 9, and I miss it. Actually, 8 and 9 here are a bad example because these were the last value I read, but let's go back here, for example. I read a 5, the producer produced 6, the producer produced 7, and by the time I wake up and I'm done from my sleep and I read, I get 7, I don't get 6. So we have two problems here. One that is apparent is a lack of synchronization. Another one that is not apparent on such a simple example is that my data could be possibly corrupted. Why? Well, in this case, I'm writing to my shared memory ints, 4 bytes long ints, and I'm reading ints. This is such a fast operation that for us to observe corruption, we would have to be extremely lucky. Imagine that instead of reading and writing an int, we are reading and writing, I don't know, 1 gig of video. Well, the operation would be a lot longer. That would mean that in the total absence of any form of synchronization, my producer could start writing a piece of video to the shared memory. Let's say that the producer has time to write half of this 1 gig video to the shared memory. And halfway through, the consumer starts reading it, and the consumer goes faster reading it, the consumer reads half the video, and then consider that it's done. What's going to happen here? Well, we are going to have corruption of data. Okay, the producer meant to send 1 gig of data to the consumer read about half of it, whatever garbage was filling the RAM after the shared memory segment after that half was read also in a swoosh, and we end up with half of the video that is correct, half of the video that is just random garbage from the shared memory segment. So it's difficult to observe with an int, but it would be much easier to observe with big video. Nonetheless, what we are going to do next, we are going to fix that potential problem by introducing our first level of synchronization in this producer-consumer implementation. We are going to use a Mutex Semaphore to guarantee mutual exclusive access. When the consumer is reading from the shared memory, nobody writes. When the writer is writing to shared memory, nobody reads. So this is going to be what we implement in version 2.